Swayam Prabha. Digital India. Educated India.
Welcome friends. Today's lecture is on GPS data processing. We know from GPS we get GPS observables which are being used to process towards finding of unknown position of points. Now finding out the position of points, we do make use of GPS observables. Now these observables may be code observables or phase observables. Again there may be different types of code observables as well as different types of phase observables. We may take either the code observables, single code observables, or multiple code observables, or single code or multiple code observables along with single or multiple phase observables. However, these observables may also be from an autonomous mode and also from relative mode. Now today's class I will be discussing on GPS point positioning. That means we will be considering the GPS observables from a single receiver and of single code observables, which is the CA code observables. As I told you, GPS positioning means determining the position of a GPS receiver using the GPS observable. It may be determined using code or carrier phase observables, and there may be autonomous positioning or relative positioning. Now in case of single point positioning, we go for autonomous positioning, in which we place a single receiver at any point, and it may be in a static condition or in kinematic condition depending upon the type of GPS surveying we are to carry out. However, one point has to be noted, that whatever is the positioning, whatever is the method of positioning, or whatever is the number of observables we do take in processing the GPS data, it is always imperative to process the GPS CA code observables. So I am be taking up the fundamentals of GPS point positioning using a CA code GPS observable. Now the from GPS signal we do get the GPS pseudo range code from say satellite I to receiver R, CA code type at any epoch of observation. So this is the notation I am using for GPS observable of CA code, that is being received by receiver R from satellite I at the epoch of observation T. Now we know that GPS observable, before going for positioning, we do go for pre-processing operation. Now this has got the pre-processed, so we will get this. We may write the GPS observable pre-processed GPS pseudo range observable may be written like this. This represents the geometric range of the satellite I to receiver R at an epoch t, and that is with respect to CA code observable, multiplied by the, along with this we have the velocity of propagation of the signal multiplied by the error in receiver clock and the error associated with the observable, and this error contains the residual error that has been present even after preprocessing as well as random error. So, this is the pseudo range observable from CA code, but if we generalize the pseudo code observable, I can write it like this to make it simplified. Now, this observable has to be processed to determine, from this we have to determine the position of the receiver. Let us say the position of the receiver is XR, YR, ZR, and the error in receiver clock error is DTR. So, these are the 4 unknown which we need to determine by processing code pseudo range observables. Now, how do you do it? We can do it by, there are different methods by which this can be processed. Of this, least square estimation method is one of the method which we will apply to show you how this is lead to GPS position. Now, in least square method of analysis, this pseudo range observable which is a non-linear, this is non-linear actually. So, first we need to change or modify this non-linear relation to linear, or it is called linearization. Once the non-linear pseudo range observable has been linearized, then we will be need to convert it to a linear model. Now, after getting it the linear model, we have to use least square method of analysis to provide us the unknown parameters which are nothing but these are the unknown parameters. So, these are the 3 main steps that has to be taken to convert these code pseudo range observable to unknown determination by least square estimation method. Now, as I told you, this is the actual or position of the receiver which we need to determine, and this is the error in receiver clock which need to determine. But initially we can assume that some value x0, y0, z0 which is the position of the receiver, that means assume position of the receiver, and DTR0 is the error in receiver clock. Now suppose this is the assumed value and this value differ from the actual value. So let us say XR equal to X0 plus del X, YR is equal to Y0 plus del Y, then ZR is equal to Z0 plus del Z, then DTR is equal to DTR0 plus del DTR. Now you can see that if we assume these values, as we have assumed these values, now our unknown is del X, del Y, del Z, del TR. Now this pseudo-range equation we can write like this, is equal to, instead of this we can write it a function which is FR, XR, YR, ZR, GTR, which are the actual these values, correct values, plus error. Now we can write this thing like this, f function I to R, instead of XR I can write it X0 plus del X, Y0 plus del Y, Z0 plus del Z, DTR0 plus del DTR plus, this is the error. Now this is the function of a function having this, so we can write it like this, f of IR X0, Y0, Z0, DTR0. Now we can see this is a function which is known to us, because these are known. So if we know the function, by putting the values of this we can get this. So this is known now, that is the computed value, computed known value, computed known. And now I can see this is a function which may be expanded by using Taylor series. So I will get d f dash fi by del x plus del fi I am dy del y plus first derivative of the function with respect to z, first derivative of the function with respect to time, plus, now you can see that this is the value which is also available from observable, this is observable, that is also known, and this is the value which is computed known. So this minus this we can do, that is known as residual observable. So actually we know, we call it residual observable, which is denoted by, suppose OI is equal to P R I R T minus function zero. So, this is the residual observable. Now, this is equal to, we know df first derivative of the function with respect to x del x plus first derivative of the function del y plus first derivative of the function with respect to z del z plus first derivative of the function with respect to time here plus error, residual error in the observable. Now, if we assume the position of satellites of the satellite I is x I, y I, z I, then the computed function we can say will be f I will be square root of x I minus x 0 whole squared, y I minus y 0 whole square, z I minus z 0 whole square plus c into dt r. So, this is the function we know. So, this is what is computed, this is the computed function. So, now if we take the partial derivative of the function with respect to x, then we will get x 0 minus x I divided by rho I. Now, this is rho I is nothing but, this part is nothing but this part. So, similarly the partial derivative of the function with respect to y will be equal to y 0 minus y I rho I r, and first function partial derivative of the function with respect to z will be equal to z 0 z I rho I r, and the partial derivative of the function with respect to time will be equal to c. This is the time. Now, we can see that this residual observable OI, here this part is this one, this part is this one, this part is this one, and we can get this thing. So, we get a observable residual observable equation, and this equation is from one satellite observable from one satellite, residual observable from one satellite. So, if we have observable from m satellites, then we can write like this. Of course, this again, now one more thing, this observable OI can be written in matrix form like this, dfi by del x del y del z dt r del t r plus our E I R T. So, this is what is the final residual observable equation. Now this observable equation is from only one satellite I. If we observe m satellites like 1, 2, m satellites, then we will get a matrix, observable matrix like this. We will get df1 dx, df1 dy, dz, and we know that df5 dt is equal to c, so we can write c also here, or we can write also df1 by dt, and here del x, del y, del z, del t are df2 dx, d2 dy, like that, df m dx, df m dy, dt, and we will have the error matrix. So we will have E1, E2, Em. So finally this is the observable equations from m satellites. Big thing again we can write in matrix form, O is equal to, this is called A matrix, X unknown matrix, and error matrix. So this is the observable matrix or residual observable matrix. This is the called design matrix because it depends on the partial derivative of the function which we are taking for measurement, and it will depend upon the constellation of the satellites as well as position of the satellites. So and the assumed position of the receiver, so it is called design matrix. This is the unknown matrix which we want to find out the unknown parameters are involved in this matrix. E is the error matrix or the residual error we have. In the observables. Now this is the linearized form, this is the linear model. So this is the linearized form and this is the linear model of GPS pseudo range observables. Now this linear model may be solved by using the least square method of analysis, normal equation method. There are many ways how this can be solved. So one of the ways is the normal equation method of least square analysis. Now suppose x bar is the solution, that means this is the right solution, then it is we get it from transpose A inverse A transpose O. So, from the matrix O already we have seen, this is known. A matrix already I had seen the matrix, and this is by multiplying this in this way, matrix multiplication, we get the solution of the unknown matrix, means we get the value of xr, yr, zr, dtr by using this. So, this is how we do find the unknown position of the receiver. This is the unknown position of the receiver, and this is the receiver clock error. Now, as you can see this, as you have seen in previous explanation, that the design matrix and the observables, these two are computed. We have started x0, y0, z0, dtr0. These are the assumed values at start. That means, to start with computations or processing, we need to assume some value for the position and the receiver clock error. Now, and this has been assumed with the basis of, on the basis of that, the design matrix value as well as residual observable value we will get, and that will help in getting new values of the position Now, after giving this as input, we will get a matrix. This will be something like x0 dash, y0 dash, z0 dash and dt r0 dash. So, this is the the value we will get giving these as the input to this. Now next in next time we will give this as the input to this and we will get some other value. So, and then again I will give this value, we will get some other value, and finally we will come the unknown value to this. So, it is the iterative process. First we will assume the value, we will find out some unknown values, which is something which we will be given to this, that will give, and this iterative process will go on till we get this value. When we will get this thing? When del x, del y, del z, del t are all will be equal to 0. So, this is the converging criteria, that del x, del y, del z, del t r is 0. In this way we determine the position of the receiver. This is the position of the receiver and the unknown clock parameter. With this I want to conclude today's class. Before concluding, I would like to summarize the class, whatever has been talked, that processing of GPS data is done to find out the unknown position of the point at which the receiver has been placed, and to find out the position of the receiver we may process code observables, phase observables either independently or together. There may be single code observation, there may be multiple code observables which may be used to process the data, or it has be like that after processing the code we can take up the carrier phase. Now whatever is the observables we take, whatever is the positioning methods we apply, the minimum thing or the first thing we need to process the GPS CA code pseudorange observables. So we need to find out the position of the receiver using the CA code pseudorange observables. There are many methods by which we do process the GPS data to find out the position of the receiver. Of this, one of the method is least square analysis, in which we do first has to linearize the nonlinear GPS pseudorange observable, then from linear after linearization we have to develop the linear model, and that model will be solved by making use of least square analysis. During least square analysis or solution, first we will assume a value, and from that value we will find out the another approximate value, and that will be iterated sequentially, leading to finally to the actual value of the position, and to arrive at the final result of the position we need to make the parameter del x, del y, del z and del t r to be 0. And since we have seen that there are 4 unknown involved in GPS observable solution, so we need to have at least 4 observables, that means observable from at least 4 satellites, and if we have more observables means satellite observable from more satellites, it will be better. With this I want to conclude. See you in the next class, which will be again on GPS data processing. There I will like to take up the GPS data processing for relative positioning. Thank you.